In this video series, starting from this video, I'm gonna be talking about how Schrödinger got his own equation. How exactly Schrödinger got it, like from his own paper. But actually, before I start talking about that, I have to assume first that you have a background in what is called the Hamiltonian dynamics and what is called the canonical transformation. You have to know about those because they are the basis for what I'm gonna talk about in this video and maybe future videos. Okay, so basically the machinery Schrödinger used in his paper was what is called the Hamilton-Jacobi equation. Hamilton-Jacobi equation. So what up with the Hamilton-Jacobi equation? What is it about? The Hamilton-Jacobi equation is just one equation, one single equation, non-linear partial differential equation, which we can write down for our dynamical system. And after that, we can solve for the different dynamical variable after, just like like Newtonian dynamics, like Lagrangian dynamics. This one just like a form, like a new formulation of dynamics, which just like depends on different bases, and the basis it depends on is what is called the canonical transformation, as we're gonna see in a moment. Okay, so what about with the canonical transformation? What is it about? The canonical transformation is the idea that we are transforming from some canonical variables. For example, if you have those two canonical variables, q, the vector q and the vector p, the vector here is just to indicate that we're talking about unmultiplied. That is, if we expand this q right here, we write down something like that. Q subscript 1, q subscript 2, and so far and so on up to qn, right? So this one right here is unmultiplied. It's not just like a single degree of freedom. And the p vector, we can write this down in the following way as well. p1, p2, so far and so on up to pn, right? So that's what I mean by the vector here. Sometimes like we want to transform from those canonical variables to some new canonical variables which are gonna make our dynamical problem a lot easier to deal with. In which sense? In the sense that they're gonna make the new Hamiltonian a lot easier to deal with, as we're gonna see in a moment. Okay, so what I mean by that, sometimes like we want to transform from those variables q, p, the vector q and the vector p, to some new canonical variables, p, capital P, and capital Q, right? And we carry out this transformation through what is called the generating function s. And this generating function actually will be a function of one of the old canonical variables, and I'm choosing here to be q, the vector q, and one of the new canonical variables, I'm gonna choose that to be the vector p capital, and t is a function of time as well. So we carry out this transformation from the old canonical variables to the new canonical variables through this generating function s. It's called the generating function or the complete integral. And in the future videos, you're gonna know that it's called the action function as well. So yeah, so far so good. Now, I mean, sometimes like I've told you, the old Hamiltonian, which is written down as a function of the old canonical variables, q and p and t, right? In general, the Hamiltonian is time dependent. So this Hamiltonian sometimes, or a lot of times, it's not going to be easy to deal with. So sometimes we want to transform to some new easier Hamiltonian, and we carry out this through transforming those canonical variables to some new canonical variables, and this will make the new Hamiltonian, and we're gonna call this k, and which is a function of new canonical variables, the vector p capital and the vector q capital and t, right? So this Hamiltonian here, we're trying all the time to choose this s right here, the generating function, so that this q right here is a lot easier than this h right here. This h right here has to be more difficult than this k right here, because that's the reason why we are carrying out this transformation. Okay. Now I wanna connect or relate the old Hamiltonian to the new Hamiltonian in just like one single equation. I'm gonna just like pull this out of my hat. I'm not gonna give you exactly the reasons why this equation is right, but just like you need to know it because that one is really important. Partial s partial t, the generating function, like you taking the derivative of that with respect to time, h as a function of the all canonical variables, q, p, and t. And that's all equal to k as a function of p, the capital B, the capital Q, and t, right? So that's actually the equation I wanted to tell you about from the very beginning, and that's the one which are gonna make an easy derivation with the Hamilton-Jacobi equation, and that's what we're gonna do in the coming video. Thanks for watching.